Have you ever wondered how the electric motor in your car or home appliance works? Well, today we're diving into the fascinating world of electric motors, specifically three-phase AC induction motors. These motors are the real unsung heroes, silently powering a vast array of machines and appliances that make our daily lives easier. In the heart of these powerhouses, there are several key components working together in perfect harmony to convert electrical energy into mechanical energy. Understanding how these components interact is not only intriguing, but also essential for anyone interested in the engineering or technical fields. Throughout this video, we'll explore the induction motor, delve into the three-phase induction motor, and discover how they work. We'll also highlight the Stator and the intriguing differences between star and delta configurations. We'll round it off with a look at the Y configuration. By the end of this video, you'll have a good understanding of how a three-phase AC induction motor functions. First, let's delve into the induction motor, the heart of many electric appliances. An induction motor, also known as an asynchronous motor, is an AC electric motor in which the electric current needed to produce torque is obtained by electromagnetic induction from the magnetic field of the stator winding. It's like the unsung hero of our daily lives, powering everything from electric toothbrushes to industrial machinery. So how does an induction motor work? Well, it's all about the magic of electromagnetism. The motor consists of two main parts, a stator and a rotor. The stator is the stationary part, and the rotor is the rotating part. When alternating current is supplied to the stator, it creates a rotating magnetic field. This rotating magnetic field induces a current in the rotor, thanks to the principle of electromagnetic induction, hence the name induction motor. The current flowing in the rotor also generates its magnetic field. And here's where it gets interesting. The rotor's magnetic field tries to catch up with the rotating magnetic field of the stator, and this results in the rotation of the rotor. It's like trying to catch your reflection in a mirror. The reflection is the rotating magnetic field, and you are the rotor. Just as you move to match your reflection, the rotor moves to match the rotating magnetic field of the stator. And voila! Electrical energy is converted into mechanical energy. The beauty of induction motors is their simplicity and ruggedness. There are no brushes or commutators like in DC motors, reducing the need for maintenance and increasing the lifespan of the motor. Moreover, the speed of the motor can be easily controlled by controlling the frequency of the supply current, making it versatile for various applications. So essentially, the induction motor converts electrical energy into mechanical energy. And that's the marvel of induction motors, silently powering our world with the elegance of electromagnetism. Now, let's move on to the three-phase induction motor. Diving into the world of three-phase induction motors, we find a marvel of engineering that significantly enhances the performance of electrical machines. Unlike the single-phase induction motor, the three-phase induction motor operates with three separate electric currents, hence the name. The structure of a three-phase induction motor is intriguing. It's primarily composed of two key parts, the stator and the rotor. The stator is the stationary part of the motor, housing the windings connected to the three-phase power supply. The rotor, on the other hand, is the moving component. Now, what sets the three-phase induction motor apart from its single-phase counterpart? In essence, it all boils down to the power supply. A three-phase power supply, as the name implies, carries power along three distinct but interrelated electrical paths or phases. When applied to the motor, these three phases create a rotating magnetic field within the motor, driving the rotor and, in turn, the motor's output shaft. This rotating magnetic field is the heart and soul of the three-phase induction motor. It's what enables the motor to start autonomously without needing any external help. It's also what ensures smoother, more efficient operation, lessening the burden on the power grid and making three-phase induction motors the go-to choice for industrial applications. One more fascinating aspect of three-phase induction motors is their versatility. They can be designed to operate under various conditions and can be customized to meet specific power and speed requirements. From powering electric vehicles to running heavy-duty industrial machinery, the uses of three-phase induction motors are truly vast and varied. In essence, a three-phase induction motor uses three separate currents to create a rotating magnetic field. This, along with the motor's robust and efficient design, make it an indispensable tool in today's high-tech, power-hungry world. The three-phase induction motor is a testament to the ingenuity of electrical engineers and a vital component in the machinery that powers our daily lives. Let's now focus on a key component of the motor, the stator. This integral part is stationary and is typically situated on the outer edges of the motor. Its primary role is to generate the rotating magnetic field that powers the motor. The stator is essentially a collection of coils wound around a ring-shaped iron core. Each coil is connected to a three-phase alternating current source. When current flows through these coils, it creates a magnetic field. However, the real magic happens when these magnetic fields start rotating. How does that happen, you ask? Well, because the three-phase currents are out of phase with each other, the combined magnetic field they produce appears to rotate. This rotating magnetic field, in turn, induces a current in the rotor. Without the stator and its rotating magnetic field, the rotor would have no reason to spin and the motor wouldn't work. So, the stator plays a crucial role in the operation of the motor by generating the rotating magnetic field. The stator windings can be connected in two ways, star and delta, but what's the difference? Let's start with the star configuration, also known as the Y configuration. Here, one end of each winding is connected to a common junction, forming a pattern that resembles a star. The other ends are connected to the power source. Now, this configuration is particularly advantageous because it reduces the voltage across each winding, which can be beneficial for starting up the motor. It's like giving your motor a gentle push to get it rolling. However, in this configuration, the current is split between the windings, which could mean a decrease in torque. On the other hand, we have the delta configuration. In this setup, the windings are connected end to end, forming a loop that looks like a triangle or a delta. Unlike the star configuration, the delta configuration doesn't split the current between the windings, which means the motor can produce more torque. It's like giving your motor a firm and steady push. However, this also means that the voltage across each winding is higher, which could potentially be a drawback. But here's the kicker. Some motors use a combination of both configurations. They start in a star configuration to take advantage of the lower voltage and smoother startup, and then switch to a delta configuration for the higher torque once they're up and running. This is known as a star-delta starter, and it's a clever way to get the best of both worlds. So, it's not about which configuration is better, but rather which configuration is more suitable for the motor's specific requirements. Factors such as the motor's size, its application, and the characteristics of the power supply all play a role in determining whether a star-delta or star-delta configuration is used. So whether a motor uses a star or delta configuration depends on its specific requirements. Lastly, let's discuss the Y configuration, also known as the Y configuration. It's a term that may sound complex, but it's actually quite straightforward. Picture three coils arranged in a Y shape. That's the basic setup of the Y configuration. These coils are interconnected at a single junction point, forming the central hub of the Y. Now, why is this configuration important to electric motor operation? The three coils of the Y are wired to the three phases of power. This configuration allows for the creation of a rotating magnetic field, which is absolutely crucial for the operation of the motor. This field spins around the stator, creating the torque that turns the motor's rotor. The beauty of the Y configuration is that it provides a balanced power supply to the motor. Each phase gets the same voltage, ensuring smooth and efficient operation. The Y configuration, thus, provides a balanced power supply to the motor. Let's quickly recap what we've learned today. We delved into the world of electric motors, focusing on the induction motor, a machine that converts electrical energy into mechanical energy. The induction motor is a cornerstone of modern engineering. We then explored the three-phase induction motor, a type of induction motor that uses three separate electric circuits and is known for its efficiency and durability. Our journey continued to the stator, an essential part of any motor that remains stationary while providing a magnetic field for the motor to operate. We also discussed the star and delta configurations, two different ways of connecting the motor's windings that can significantly impact its performance. Lastly, we touched on the Y configuration, a specific type of star connection that offers its own unique advantages. With this knowledge, you now have a better understanding of how your everyday appliances function. Thanks for watching.